I think that should get everyone set up. Seeing advanced repairs for gas turbine components, March 2023.
Yes.
All right. Well, thank you for having me to provide this presentation. I'm, in fact, beaming to you from Ontario, Toronto, Ontario, just down the road from Dundas, where Liburdi Turbine Services is located, and I'm part of that team. Unfortunately, I'm going to have to start the meeting with a bit of a sad note. 2 weeks ago, our founder, our mentor, our leader, and our friend, Joe Liburdi, passed away. So this will be my first presentation given really in memory of Joe, and trying to show off the things that he's instilled in our group to develop advanced repairs. You'll ask the question, that's a pretty old picture of Joe that I've selected there, but it kind of is apropos for our discussion. This picture comes from his 1977 paper on rejuvenation of used turbine blades by hot isostatic pressing. And so, as you can see from a little clip of the cover page of that paper, he was a member of the Westinghouse team that was located in Hamilton, Ontario, Canada, just near where Dundas facility is. But he saw some opportunities where he wanted to extend the life of gas turbine components, and also saw that that wasn't going to be possible within the walls of the Westinghouse Canada facility. So he set out a couple years later to make Liburdi Engineering. So it's a privately owned independent turbine component repair service provider. I think I really want to show off what Joe's created as part of this in memory. Yeah, my first plan was to delete all this for a technical presentation, but I just want to show it off for people who don't know Joe and what he's done. We're involved in servicing oil and gas, power generation, and aerospace with repairs and new make component processing. And we also have an automated welding division for aerospace, nuclear, industrial applications, which we'll touch on later. Our primary facility is in Dundas near Hamilton, Ontario. And that's our head office and repair facility, but we also have an automation division across the street, just across the highway really, but in Hamilton. And then we also have a facility in Mooresville, North Carolina, in the heart of NASCAR. So what we'll be talking about mostly today is one of the divisions of Liburdi Engineering is turbine services, where we're industry leader in development of advanced component repairs. So only source for rejuvenation technologies. We do blades, vanes, and combustion components. And quite interestingly, we kind of get to touch all different OEMs. So we work on GE, Rolls-Royce, Siemens, Westinghouse, Alstom, Dresser-Rand, Arena, Mitsubishi, Solar, all sorts of things. So we get to see all the things that work and all the things that work better. Engineering side, because the company was born from a metallurgy side, there was a component life analysis role there, but also failure analysis, coding evaluation and selection. And then we get into component design where we're supporting companies on that, but also engine health and performance monitoring, which is an important part of the work that we do. And then some training seminars as well. Our automation division grew up in the 90s, and it's an industry leader in automated welding systems, and that's for turbine, aerospace, and then industrial and tube mill applications. And the pulse weld system is renowned for its accuracy and repeatability in the microplasma world. And so every major turbine OEM is using our systems as part of their either new make or overhaul processes. But also we're a pioneer in development of orbital welding systems. So there's portable tube welders, the gold track welding systems, and precision welding systems for tube and pipe, medical and power plant, nuclear and automotive, all sorts of things, and a lot of really niche welding projects that are pretty exciting. So So just a little bit more about Liburdi Turbine Services. We're certified in AS 9100, ISO 9001. We're a Transport Canada facility, which is the Canadian FAA equivalent. There's some agreements between those two groups that we are able to do book repairs there. And then we're NADCAP certified in 2 and soon to be 4 different processes. So a big part of what Liburdi Turbine Services does is committed to reliably extending the life of gas turbine components, and that's through advanced and conventional repairs. And so we really like to look at this in the circular economy model. And you can think of the typical model for components is extract or take the material, make through the manufacturing, and then break or throw away at the end. It goes to landfill. What Liburdi hopes to do is to make sure that this service circle, which is really the smallest circle of the circular economy, and it's the one that requires the least amount of additional resources and is the lowest cost for the operator of, in this case, the gas turbine, is to make sure that we can make sure we get as many laps around this circle as possible. So an example is some components on the first repair after 24,000 hours, they'll have a recoat, and then on the second repair, they're going to get rejected. And that's not all components, but it's just an example. And so what Liburdi's done with some of these components is we'll do a recoat repair, just similar to other repair vendors, but we'll also really look at the future of the component, making sure that it's adequately coated, so that there's no degradation of the external features, make sure we're not removing unnecessarily any of the wall thickness of the component, and then the next time through, we'll rejuvenate. We'll get onto that a little more. That was kind of linked back to Joe's paper. And then we'll do it again. We'll recoat and then rejuvenate, because each time we rejuvenate, we're returning to the original material properties, so we can extend that. And so try to show this circle getting slightly smaller. There are some parts that are going to drop off for different reasons, but the hope is that as many laps around this this service circle, that means the operator's saving money. And I guess from the environmental perspective, we're reducing the raw material extraction for those components. So this is just kind of a detail to give you the different engines that we touch on. Okay, it's all across the world, but here we have aeroderivative here with LM2500 and the SGT A35 or RB211, a lot of power turbine work that we do, some flight repairs on PW2000 engines, but then the frame engines, so the typical GE frame engines here, as well as owing to Joe's legacy, a lot of experience early in our career on the W191 and the W251 engines, and then kind of more recently, more time spent on V84 engines, I guess then V94 as well, and then the Alstom Type 11, which have been pretty exciting for our team down in Mooresville, where the singular combustion sections, they're involved in doing the coating and repair of those, and they get, when you got a component that you can walk around in, it's a little bit different than the aeroderivative parts that we do a lot up in Dundas. So what I'd like to do is just to touch on 2 enabling repair processes that we use at Liburdi to extend the life of gas turbine components. We're going to talk a little bit Liburdi powdered metallurgy, or LPM repairs. The LPM is a higher strength alloy than typical weld alloys, and usually you're going to see less distortion. It's a solid state liquid phase sintering process for superalloys, and what that means is you don't have a local heat like you would in a welding process. And there's certainly areas on all components where welding is the appropriate, and we also often do hybrid repairs, but there's also areas, large areas for wall thickness recreation where you just would never want to do welding because you'd have way too much distortion, especially on the aeroderivative components that we're going to talk about today. So this incorporates both solution and age heat treatment cycles within the process. And so we've been able to do vein reconstruction and even casting recovery. So we have both a flexible tape and a putty, which we'll get into a little bit. And then we'll talk a little bit about throat area restoration with tape materials, and then wall section recovery and thickening of thin vein walls. So I think the main thing here is we kind of talked a little bit about these things, but we've even used this in new part manufacture. So that's on HPT blade tip closures, where they're concerned about the stresses caused by local welding. We've also done abrasive engineered HPT tips that have abrasive that will cut into a seal and provide better clearance control. We've done that, developed that with an OEM process and created the equipment to do that process. And then more recently, we've been involved in reclaiming defective castings prior to getting machined into the final component to replace some damaged or missing material. So I'll just step into the process a little bit here. In the top left corner here, you're going to see at incoming, and this represents a deep crack, and this represents some corrosion or oxidation damage on the surface. And so the difference than typical braze processes is that we'll actually remove all of the damaged material all the way to the bottom, and we'll also do additional inspections to make sure that crack is right out of the material, and then make sure we're also removing any of the denuded material on either side of that crack. And then we're going to put in our LPM material. So we have a high melt alloy, which is this putty that goes in first, and then a low melt alloy that goes in on top. So the putty is just like, I don't know, Play-Doh that you can form into those prepped areas, and then tape that you can roll out and spread across an area. I'm going to just go into, before we talk about what after being heat treated and blended, is what happens at this arrow here within the deposit. Down here, you'll see the green areas. And so these are just balls of super alloy. And what happened as they're brought up to temperature during the consolidation heat treatment, they actually get partially sintered together, and it's going to form a bit of a lattice between those balls of super alloy, and that gives it a little bit of strength as it goes up to the higher temperatures. And then what happens at a certain temperature, the low melt alloy is going to infiltrate into the interstices between the high melt alloy balls, and then it's going to be held there for a period of time where you also start to see diffusion, from constituents from the braze into the base alloy, high melt alloy, and then the other direction. And then eventually you get a diffused super alloy material. And then our last step is to heat treat and blend that surface back to shape, blend or machine or even form, as we'll see very shortly. So this is just a picture of a through wall damage on a leading edge of a vein. Here you can see the LPM material and the base alloy, and it's got a typical braze structure, but generally you're going to see less porosity than on a typical braze repair, and that owes to the two-part process that we use. And here you can see after machining, we've got the wall thickness built up to the original size, and yeah, this is ready to go back into service. Just to give you an idea of some of the depth that we work to, so this is 3 millimeters thick and 4 meters thick to the bottom. This is, we apply material, and I'll show you some pictures on this in the next slide. Apply material to the seal slots and do a build up, and then re-EDM that seal slot back into shape. Let me just touch on the tensile properties before we show you some more about that repair. So I think that the key thing is not everybody has all of the mechanical properties memorized for all these components. Generally, the ultimate tensile strength, the yield strength, is going to be higher than the typical weld alloys that are used on a lot of repair shops because they're easy to weld and can build up material easy. But I think the key thing to show here is that we're not just doing kind of small little repairs. We're testing these at 250 thousandths of an inch or 400 thousandths of an inch wide. So you can see in here, this is a cyclic test bar that we've put together, and you can see the 1/4 inch LPM deposit here in the middle, and that will run out to understand the fatigue resistance of the component. So I'm going to try to answer a few questions that people may have about this repair, so I'm going to try to touch on what is the maximum repair capability, i.e. maximum defect size and wall thickness, and our repair is limited to featureless internal walls, and our component edge repair is possible. So I'll show you some examples that this is where it all gets interesting. It's no longer cartoons, it's on actual parts. So this is the part we saw these two pictures earlier on. I think the one thing that I missed highlighting is this gorgeous interface between the LPM and the MARM 247 material etched up that you see no porosity or no deleterious phases. Here you'll see this is where we're starting with an oxidized seal slot face. And what we haven't shown you in this group of 3 pictures is when we prep this, then we're going to open up all of these seal slots that are here and remove some material from this wall. And then we're going to build it up with the putty material. This is actually after LPM's applied and after it's been consolidated. Then it will go through a number of machining processes, both to machine this surface here, as well as to EDM in the seal slots. And that's what you can see. This is that deposit. Would it be a section right through here? Most likely, where you're seeing the LPM on both sides and then the seal slot down the middle. So we really look at this as a reconstruction repair, something that otherwise would be scrapped off or left for no more service. These parts may be familiar to some in the group. On the left here is an RB211 or SGT A35 component. Here we're doing a very heavy repair on the leading edge. This is where many of the cooling holes had shown either cracking or oversized condition, and we're opening those up and preparing those so that we can completely refill that leading edge so it was like it was cast. Like we're not trying to line up previous cooling holes. We're just resetting the entire surface, and you'll see that in a second. Here on the right, we have an LM2500 HP1 nozzle. Lauren from your team, I think he was on the call a moment or two ago, but he gave us a nice presentation maybe 2 years ago just on the LM2500 and his experience in the U.S. Navy running these. And so this was actually a U.S. Navy component that had very, very heavy damage. And so what we've done is as I mentioned at the start of the process, is we have to remove all that damage. We can't leave it there and think that we're going to be able to repair it. And so there's damage all the way along the cooling holes. So we're routing them out and opening them up, and then preparing also the leading edge surfaces for LPM. This is the next step for both veins. Now we've applied the LPM on the leading edge, and so it is just like what I said. It's putty. It's super alloy contained in some solvents as well as a plasticizer to be able to get it to stay in position as we run it up to temperature in consolidation. And we've done the same thing on the HP, the LM2500 nozzle here, but really to a much greater extent in that we're doing a full wall thickness repair across that entire surface, and then repairing each one of those groups of cooling holes all the way through. And then the white, what you see there is just a stop off, is to try to keep a group of cooling holes that are adjacent to the repair surface, just to make sure we keep them open during the repair and don't have to do some additional machining that's not necessary within the work scope of the repair. After consolidation in the heat treatment, here's some pictures, and now you can see that leading edge that was once full of cooling holes, no longer has any cooling holes, and it's pretty neat to see. And that LM2500 part, all of the shower head cooling holes on the leading edge, as well as all of the cooling holes along the concave surface of the part are filled up with the powdered metallurgy. And so this is the exciting thing. Afterwards, we have a lot of machining to do. So we use either sink EDM or fast hole drilling, or sometimes EDM milling to create these diffused cooling holes on this component, and then the rest of them are just straight through cooling holes. But one of the cool things here is that we're able to return the size back down to nominal position. What we see during operation is those holes will tend to get slightly larger, and as they get larger, you're going to see some degradation. There's going to, redirect cooling flow to that leading edge as opposed to somewhere else. So that's an important part of why we do the repairs on less so maybe RB211 that doesn't have an airflow requirement, but LM2500 that does, and that allows us to meet the criteria to go back in the engine. So yeah, maybe I'll just stop there on the HPNGV, and that becomes, I think one thing I missed highlighting here was you can see the etched surface. We've specifically etched this up so you can see the repair area here on the leading edge, and that's where all those cooling holes are replaced. You can also see a repair that we do along the, these parts are originally brazed together, and after processing they kind of, that braze degrades with each processing run. So we do almost a pre-repair on that surface to make sure that that doesn't become a problem in service. Less so a problem through this area, but we have seen it be a problem at the trailing edge. So here's a maximum repair capability of a seal segment. This is a real good example that we have of remanufacture of a gas turbine component. Here you can see there's a swath where some hot gas come across these IP seal segments, and it's degraded that material. You can see there's some missing material in between the seal here, and then if we look on this view, you can see that the seal has been opened up. Here's about the nominal thickness, and then over here it's been opened up where oxidation has taken away some of the where some of the materials oxidized and spalled and is no longer there or useful. The other thing we see with these components is they actually deform. And so through engine service, they're held here and held here, but we'll see some deformation. That's the red line where they've kind of cupped or bent out of shape. And what we do is we do a straightening operation, but for our repairs, even more exciting, is everything where you see this kind of jaggedy view here, we're actually prepping all of those surfaces. So that's the entire gas path. So from this surface all the way through here is all the gas path surface. A little bit of that is covered by the honeycomb later in its process. We'll then also prep the side of the face and open up the slots. And with that, we're able to push our LPM material into the slots to totally close them up, but we're also adding LPM material from this surface to that surface. And then we're taking what was once a cast surface and running a CBN grinding wheel along that surface that machines from here to here, all in one operation, and machines all of the geometry that will then become the gas path and honeycomb location features. We've got a little bit of extra EDM work to do to make a seal, but I think the key thing for this repair is re-EDMing out these seal slots. And what that allows our overhaul shop that we support on these repairs to do is that they can put a brand new part against a repair part, and they slot together like two brand new parts, because they're all machined. These seal slots are machined with respect to their as new datums, and they slot together quite nicely. And this is really important if your repair yield isn't 100% and you've got whatever 32 repaired parts, and you're trying to put two brand new parts in there, you're going to run into trouble unless you do this full repair. And they've really been happy with this because that means their assembly work goes very quickly, and they don't have to be fitting seals or blending material off seals to get the old part that's been slightly deformed and not fully repaired to made up against a brand new part. Now we'll go into some maximum defect size repair capability. This is an IPNGV that's had a FOD event where the leading edge has been hit with a turbine blade. So typically this part would just be thrown away. We were asked by our customer, is it repairable? And we said yes. The real key thing for this repair was there was a limitation that it had to, the repair had to have the internal wall feature. So typically on the external, it's pretty easy to do the machining so you can match the wall features of the external feature. But you can see here that there's some cooling fins along this surface and along the leading edge. And what we've done is we've cast a ceramic core, just like a new make casting process, and then we're able to press our LPM material around that leading edge, and then we've prepped up and around that, so we're building up the whole leading edge at the same time to execute this repair. And so now we'll kind of look at the repair. This was a really exciting one that it came back to us after 24,000 hours. You can see inside here where the internal geometry of the ribs moved from the base alloy into the LPM alloy. But the really exciting thing here was 24,000 hours, no cracks, no deformation, no damage, and we just recoded the part and put it back into service for the next 24,000 hours. Some other things that we get involved in, this is just the casting that we talked about. Sometimes there's some internal rib damage. These parts, yeah, the internal geometry of that must be at the correct temperature for type 1 or type 2 hot corrosion, and we get a buildup of the deposit. And certainly we know that we have to remove that deposit, otherwise it will just continue to eat through the wall thickness of the part. Sorry about that. What we've done is we've made some tools. This is just an example of an early one to roll out that geometry with our LPM material and build that back up where we've had to remove some of this damaged material. We talked a little bit about throat area repair and then repair directly to a trailing edge. And so I wanted to show a couple examples of that where we're using powder metallurgy on this surface. And you can imagine if you were measuring the throat, it would be between this trailing edge and the adjacent airfoil. And so we can adjust that by adding material if it's been worn away through subsequent uses. And then you can also see that we're doing a full trailing edge repair and a partial trailing edge repair on the platform as well. And so then after it's run through service, you can see here, this is the repair right to the trailing edge, and you've got a clear repair there. And then after coated, you've got a geometry as expected to go back into the engine. Often you'll see a slight discoloration or different color for the powder metallurgy repair and the base alloy, depending on how close they are in composition. And then the final one, the Avon components, SGT A20, they have run for a long time and often come in where they won't meet their throat area requirements. So we've done this repair on those for a number of years. We're adding the LPM on the trailing edge to recover that damage. So we've talked a little bit about a typical enabling technology for non-rotating components, and now I'd like to kind of bring it full circle to what I mentioned as Joe's paper from 1977 on rejuvenation, what we call full solution rejuvenation, or FSR. And so basically what we're doing is returning turbine blades back to 0-hour life. So this is a full solution rejuvenation. We're taking that material above the solidus temperature and then holding it there for a period of time and then dropping it below, and then doing our proprietary aging heat treatments to develop the primary gamma prime and a secondary gamma prime structure, and that could be 1, 2, 3, or 4 additional heat treatments afterwards, after this full solution. And what we're trying to do is restore the microstructure and then therefore the crop properties, primarily the creep strength. And so we've if rotating parts exhibit good wall thickness and no internal degradation, that would be oxidation, IgA, or other deleterious phases, then they're good candidates for FSR. So I'll go into that a little bit about what we're dealing with. So I'm not a metallurgist, but if you work at Liburdi, you have to pick up quite a bit of that. My background is in mechanical, but we'll start with the metallurgy and move to the mechanical for what I imagine most of the team here at ASME are. But here we have a blocky gamma prime structure. This is the as new. And how do we know the as new condition is we can look at the root of the turbine blade, because that hasn't been exposed to the high temperatures and so won't show signs of aging. And so this structure is what we could expect that the rest of the blade had when it was manufactured. After 24,000 hours in areas on the airfoil, you're going to see some amount of agglomeration. So you're going to see slightly more rounded gamma prime particles, and you're going to start to see agglomeration of these secondary gamma prime particles. After 48,000 hours, you're basically seeing spheres, no sign of the secondary gamma prime particles. And as we maybe can remember from our metallurgy course, any dislocation moving through this material, it would take more energy to go up and around a blocky gamma prime particle than it would to go around a sphere. It just takes less energy, and therefore you'll see that mechanically, which we'll see on the next slide. And then the key part of the full solution rejuvenation is our goal is to take this microstructure, take it above the solution temperature, and then reprecipitate out the gamma prime structure. So we get this blocky gamma prime structure and this secondary gamma prime structure to make sure we're not only returning the creep strength, but also the tensile and fatigue properties of the material. And I don't expect these numbers that I popped up on the bottom of the screen to mean a ton to you, but for the RB211 and Avon engine, we have authorized repairs that have been authorized by the OEM. We're an authorized repair vendor for those, and these rejuvenation repairs have been authorized for them, and we've been providing them for since 2002 for quite a number of years. So we talked a little bit about the metallurgy. Now we'll get into the mechanical. So here we're looking at a stress rupture test, hours to test, what, maybe 44 or so. The most important thing is it's above the 23-hour new material minimum spec for this alloy. So what we'll see after 24,000 hours of service, you're going to see some of that agglomeration of the gamma prime structure, and you'll start to see the time to stress rupture drop on that material. Not a big deal, can continue running in service, and that's expected. But after 48,000 hours, you're going to see a significant drop from the new material minimum. I wouldn't say this is a precipice that it's going to fall off and the parts are going to damage, but sometime in the next cycle, or if not that one, certainly the next one, you're going to run into trouble where you could get creep voids and then a blade rupture. And so these kind of line up to the pictures we were looking at before, and then after FSR, it returns. It's not a big deal. This is just data, so I can't change it, but it turned out that our stress rupture test ran longer than the new part material, but really all that matters is that it's above the new material minimum spec after the full solution rejuvenation. So I've got a couple slides here to wrap up. Once you eliminate creep life as a life-limiting mechanism for a turbine blade, because you're able to do rejuvenation and return them to service, you're just basically shifting what the life-limiting feature of that component is. And especially for aeroderivative components, often the wall thickness is going to be that next life-limiting feature. So we've developed using computed tomography and inspection method, where we're going to look at each section thickness, and then it's going to give us a picture or an image of what that section looks like, and then we can evaluate it using a number of macros that we program. And I'm just going to click to the next slide, which will show you the minimum location. So we're going to look within this section and this section and this section all the way around the turbine blade, and they'll likely have different limits as to the maximum and minimum condition in there. And then the software helps us to pick the minimum, and you can see the white dots around the internal and external surface. That's showing where the minimum ray from the external surface to the internal surface, or the internal surface to the external surface, gets the minimum wall thickness. And then we can compare that against the criteria, and most importantly, reject parts that shouldn't go back into the engine, but not call parts just because they've run 24,000 hours if they still meet the dimensional requirements. So just to wrap up, the piece of equipment gives us an opportunity to look at the internal features of the component. So I'd like to take you to finish with a tour of a RB211 SG A35 component. So this is not a CAD model. This is a scan of an actual part we had in for repair using the computed tomography machine. And you can cue, if you want, the 2001 Space Odyssey music here, as we're about to take a bit of a tour on the internal of the part. So just spin around the internal, shows you the external geometry, but we're just going to go up where basically following as the cooling air flows up the leading edge of the component, start to see all of the cooling holes that enter from the external and out through one of the dust holes that allows the any dust that gets into the part to get removed. And then we'll just slide down and show you the different sections through the blade. And what this allows us to do, we'll build that back up, not using our typical approach of additive manufacturing that comes from our automation group, but just re-show you that model. But what this gives us is a capability to look and investigate if there's any internal features or mismachining. Some of those cooling holes out of position are coming in through the wrong wall. We'll be able to see that with a full scan. So admittedly, most of the work we do is looking at individual scans, because in general, we're looking at wall thickness measurement, but it's also pretty cool to be able to give people a tour of one of their turbine blades. So that's a fun thing that we like to do. So I hope I've been able to give you a little bit about some processes that we use, what we call is enabling technologies that we use to extend the life of gas turbine components, and giving you a bit of a background of why, the ethos of Joe Liburdi's vision was to provide value to the customers. Customers already purchased these components, and it's up to us as repair vendors to make sure that they can get the most trips around that little circle in the circular economy around that surface. If the part doesn't need to go in the garbage and still has life, we'd like to make sure that you can save money and keep running that. So that's our approach, and thank you. Hope I can answer any questions for anyone.
Scott, the first question here was about recording. I did record the Zoom session. I will send you an email tomorrow and ask if it's okay to post it on our YouTube page. So take a look at it across the night and tomorrow, and see if you feel like it's something that you wouldn't mind being on our YouTube page. If that's the case, fine. If not, then that's okay too. Sometimes we can post, sometimes we can't. Okay, so take a look at that and think. And that the one question that's in the chat is, can I see this as recording? So let's find out about that tomorrow, and then we can decide what to go from there. I have PDH certificates, both in paper and as PDF for anyone that's online. Does anyone else have any questions for Scott?
Oh, I have one, Ellen.
Oh, all right. We have one in the audience and one from Lauren.
All right.
All right, let's see.
Scott.
All right,
Scott,
Lauren,
thank
I'll tell you what,
so
let's
much.
let Lauren go first. Go ahead, Lauren.
Okay, thank you. Thank you very much, Scott and Ted, for being prepared to do a speech almost like at the two week out point. We really appreciate it. Could you explain just a little bit how you do any kind of flow testing or flow validation, just to validate that the cooling holes are all basically flowing at the right amount?
Certainly, we do two processes. One is more of a qualitative process where we have some tools to put pressurized water through the holes, and what we'll do is we'll look down each row of cooling holes and make sure each one of those is flowing, not just flowing out water, but shooting out water, if you will, so that it's got full. I'll call that a qualitative process, but certainly on the LM2500, we also do a qualitative process where I don't think I have any good pictures that show the top of the part, but on the top of the part, there's two cavities. One that's fed from the ID, and that's the leading edge, and one that's fed from the OD surface from the trailing edge. And so we'll have an instrumented flow test stand that will calibrate and prepare, and then we'll basically put these parts into a fixture, and then we'll hold them up, that will seal around those insert cans, or sometimes we also do these inspections in process with the insert cans not installed, and we'll flow that material, that air through there, and then just make sure it matches what we would see out of a new or serviceable component.
Okay.
Excellent. Thank you so much.
Cheers. Thanks, Lauren. Good to hear your voice again.
All right, we had two questions in the audience. Scott, who wants to go first? All right, speak up, please.
Dimensional accuracy of the average guys have for dimensional accuracy. Because I know once an object is sintered, or it goes through the sintering process, it's more likely to form and just lose its dimensional accuracy at the end. So you guys have like measurements, or do you build up to a certain point to make it almost exactly the same, if the product exactly the same dimensional specs as it was before?
Did you hear the question, Scott?
Okay, I might have missed a tiny bit, but what I'll do is I'll answer what I heard, and maybe just missed it a little bit at the end, or at the start, sorry. I think the question is about dimensional accuracy. So if we're looking at this surface here, or this surface here, are we doing that? I wish I'd included it. It kind of got cut out to make time. As we use CMM inspections, both touch probe and laser scan to evaluate the buildup, to make sure that we're essentially smoothing to contour. In addition to contour gauges to evaluate that, and that's something that we definitely have to take into account, because we're adding material in a manner and greater than what would ever be expected. So we have to develop our own processes to keep those within tolerance. So we'll do some where we scan the component before we do the repair, and then scan afterwards and do some comparison. Some of it we're comparing to parts are so damaged that we're actually comparing to a master shape and making sure that that meets criteria. So yes, through three techniques, CMM laser scan, CMM touch probe, and contour gauges we're using to verify that we have the surface contour correct. And then we're also, maybe one other step that influences that is we do wall thickness measurements along you know, for example, all along this surface and this surface, kind of just outside of the cooling holes, we'll use ultrasonic wall thickness measurement for those locations, and maybe eventually we'll be able to figure out how to get it onto our CT machine, but it's a little underpowered for these two airfoiled vanes to do that reliably. Maybe the first question I should ask is, did I interpret your question properly from missing a couple of the words?
Yeah, for the most part, yeah, that's pretty much what I.
Yeah. Yes.
Great, thank you.
Question. Oh, yes, I was trying to find the AS number for the specific questions to ask. So last year I was lucky to go to Collins Aerospace for an internship, and I got to learn a little bit about AS 9145, which is an advanced product quality planning, which is APQP.
Yes.
I was wondering if you guys are, I know it's a very new standard in aerospace. It's more integrated in manufacturing for auto mechanics, for cars. I was wondering for new parts specifically, and even for old parts, especially when dealing with service and maintenance in this last step, how are you guys working into adopting this new standard in aerospace?
Yeah, certainly. It's actually just released. Well, I don't want to say just released, but just required now this year is AS 13100, which is actually a combination of AS 9100 and the AS 9145. So it includes the kind of the first stage of the ISO part of the quality qualification, but also includes that APQP as well as a number of other those other steps that you're quite right were a key part of the automotive side that's moved over onto the flight side. So I'll just explain that we have introduced that concept at Liburdi, and it is part of our design control process. It's optional on some of our industrial repairs, but eventually, as we further adopt AS 13100 within our organization, will eventually be the standard that all components are developed to. Certainly, anything that we've done that's supporting new part manufacture. One example is we use our automated welding machines as part of the new make process to weld up hard face locations on some turbine blades, and that one required us right from the start is to jump in and that essentially the S9145 APQP process, and our standard requires that any of our flight repairs, when we're developing a new flight repair, it also follows that process. So yeah, I'm glad you asked that question, because it's definitely something we've been spending a lot of time on recently in developing that capability within our organization, understanding the DFMA, FMEA, and PFMEA, and then the measurement systems analysis and all that, all those steps that we probably did in a way, but we didn't record them exactly the way that it's now required by the AS 13100 standard.
Thank you so much.
Cheers. Thank you for the question.
All right. Any more questions, either online or in person? All right, Scott. Normally you would get a free meal, but you are online. We're doing something different tonight. But someone hopefully has your physical address.
Yeah.
Yep. And we will be sending you an ASME gift. And thank you for speaking tonight. And I can't tell you how much we appreciate it. This was something new for us. We normally go to a manufacturer. We have a manufacturing tour, and it was a dinner, and then we have a speaker from that same manufacturer do the presentation. So this was the chance for us to come out and visit the students, and it's been really great. Our events are on, they're posted on our ASME section page. They're also on Eventbrite. You can search for our Eventbrite group, ASME Apollo Guest Servant. We also have the YouTube channel, so you can look there. If you can't get to the event, it's okay. You can get the Zoom link and join in anytime you want. You won't be able to go on the manufacturing tour. We don't film those, but you'll be able to join the presentation at 7:30, just like Scott joined us. Jack, do you have anything you want to add?
That's all I got. Thank you very much, Scott. Appreciate it.
Yeah, we'd like to do another student event again sometime soon. It was really great visiting you here.
Cheers. Thank you. I'm glad I included a tour in my presentation of the turbine blade. So it was, you can put a checkbox in your APQP requirements tour, and you can put a check mark in that one.
Sure. Thank you.
All right, thank you. All right, keep in touch, Scott.
Cheers. Thank you. Bye-bye.
Well,